Tech, Landau Institute. Professor IGOR LUKYANCHUK from France made a lot of nice stuff, outstanding, and taken part in some key discoveries in graphite, graphene. And today he'll talk about his new adventure, Ferroelectric world, please.
Okay, thank you. Actually, it's now for 20 years my main subject, and I will give, as organizer asked me, 2 conferences. The second will be not in August, but August 20. So it's, sorry? Or can be moved, so we are very relaxed. And just I don't know why PowerPoint decided that it's August. So, and today I will speak about some statical properties of ferroelectrics and nanoscales. And actually, because also we quite relaxed in subjects, I decided to speak about this subject because of the very nice place. Thank you very much to this institute and very high audience that actually I really had a dream to speak with such audience, because usually the people in Ferroelectric, they are quite in delay with respect to all the world. And this subject is more, I think, interesting will be to general audience of theoretician than to the particular people who are working in this. So actually what I would like to convince you is that ferroelectrics is a topological materials, very interesting, and there are a lot of very deep physical properties. I will not even have answer on all of the stuff that I will speak now, but I think that there is very not yet explored background, topological background in this stuff. And somehow I'm trying to convince Landau, because he always told that ferroelectrics are not interested for theoretical physics, because they have very particular material properties. So we shall try to look for the general properties. Actually, for the general audience, let me tell some well-known stuff, that ferroelectric is a material in which the spontaneous polarization appears as the order parameter. So here some kind of realization. Of course, there are a lot of different types of ferroelectrics, like magnetics, and this is so-called perovskite material, which have the cubic symmetry, and the driving atom is an ion of titanium, positive titanium atom, that spontaneously move off center, creating the polarization, spontaneous polarization. So displacement, microscopical displacement of central atom give us the spontaneous ferroelectric polarization. And like no, there are quite different. Titanium frequent, but there are also another examples of the central atoms. Well, it's a question that is widely discussed, because there are actually two type of hypotheses, and possibly the mixture of them is the truth, because one people told that you have a lot of already potential minima around of center, and just usually above transition temperature you have some averaging of the polarization, and after it occurs like order disorder type of transition. And another people talking that it's mostly displacive type, but it's not. I would like to tell that it's not very clear up to now, and it seems that both mechanisms are working. But also I should tell that the microscopic theory is much less developed, let's say, than in magnets possible. So first of all, of course, because we have all the parameters, we have subhysteresis loop, and this is oversimplified hysteresis loop. So it's polarized by electric field to apply potential. So this is the hysteresis loop, and I show you the most simple case when you consider only up and down polarization, but in principle, if you have really cubic symmetry, you can have also another direction, and we shall widely discuss this more realistic case. So, well, the ferroelectrics, they seems, it's not also, of course, the subject of this conference, but it's always needed to tell that they're very important for the applications in principle low dissipation electronics, non-boundary computing, terahertz technologies, and so on and so on. Possibly the main advantage of ferroelectric with respect to the materials that are based magnetic or which are based on the electrons, that we have really ion motion that is very resistive to any type of radiation. So this is very good to put in the satellites and the aerospace industry for military applications and so on. But of course, we shall not discuss this too much. It's completely different engineering stuff. Just I would like to tell that there are a lot of attempts to use ferroelectric materials for the memory. It's called ferroelectric random access memory. It does not work too much well with respect to its competitive magnetic memory. There are possibly some historical reason or some market reason or some technological reason. Also, it's very difficult for you start to speak with technologists to understand what they really need. So, but this idea always existed. They have a very rich story that I will tell after. What we are now possibly more interested in speak about some kind of theory and theoretical approaches that can be used for ferroelectrics. And now, the approach now is the ab initio modeling. So the people really succeed to do some modeling of the appearance of electricity, but they're using some box with some not quite clear code, and it seems that it converges by some fitting with experiment. But anyway, for me, it's some kind of experimental physics, and we always also trying to understand what they did, how they are close to experiment, but they absolutely give no idea what really happens. So the most really important approach that was used and most reliable here, as I told you, microscopic theory is very, very difficult. There are no, I would tell that there are no really very great output from the microscopic, but phenomenology works well, and Ginsburg-Landau approach is also the main tool to study the ferroelectrics, but the important things that make it different from all other materials, the electrostatic is strongly coupled with other parameters, and it should be taken into account. So, and it's, let's say, my suggestion to use some kind of topological description that possibly makes the situation more clear. And about of this, concerning this, I will talk later. So, but possibly some qualitative descriptions that take into account mostly global behavior of the parameter can be qualitatively more useful than Ginsburg-Landau approach that become today very complicated stuff. So let's now look for the equations. So, well, it's conventional Ginsburg-Landau equations that everybody knows. The point here, first of all, is one component, so this is oversimplified theory just to start the introduction. But the point here that in majority of ferroelectrics, the phase transition is the first order transition, but not the second one. Usually it's the first order transition, which is very close to second order transition, but it's still first order transition. The origin is interaction with some elastic degree of freedom, and the people model this first order transition, taking the first order coefficient in this case is negative, but as I told, it's in certain cases it's first, in second cases it's second, so the sign can be different, and to finally stabilize, the sixth order coefficients is added that in principle it fit experiment quite well. But this is, I mean, this is just a first, let's say, difference from conventional Ginsburg-Landau, but not last and not the most important one, because actually there are different effects that make the theory much more complicated. First of all, as I told you just from the beginning, usually what is most, but it's not general rule, but what is not, the people optical is most important for industry, for technologies, and also which is much more easy to obtain as a samples. Usually is a cubic perovskite, which actually have different directions of the displacement of the central titanium atoms. And even dependent on the material and dependence of the condition on the temperature and many other factors, one can have, for instance, displacement up-down. In this case, we shall have six equivalent direction, or we can have more equivalent direction because we can have some kind of so-called orthorhombic phase when the central atom will displaced in the direction of non-principal diagonal, and in certain cases the displacement are done according to the principal diagonal, so it will be 8 equivalent directions. So this somehow depends on the material, on the conditions, and even sometimes the clumped and free material can give the different displacement of the polarization vector. But the degeneracy, what is important to us now, that degeneracy is quite high, and even there are materials where can be somehow in between of the situation, so we can somehow make it more isotropic. And of course, this is very important and very interesting to have the almost isotropic ferroelectrics, which is in certain sense beyond some liquid crystal, because it's can give very interesting things. The second aspect that is very important, that actually the displacement of the center of the polar atoms is strongly coupled with elasticity, and the deformation are quite large. So this is something like 0.3%, which is huge value. So the elasticity is strongly participated in the phenomena and the crystal, and because of this, one can, the inverse side of this, we can really play with, make some tuning of the phenomena also by some kind of stress, strain, and so on. And the last one, it's B, so it should be C, which for me possibly is most interesting, is enormous coupling also with electricity. Actually, polarization produces charges. The most easy to see because charge is divergent speeds from electrostatics, and the most spectacular effect is creation so-called depolarization field. So if polarization, let's consider the finite size sample with surfaces, and polarization will terminate at the surfaces. As a point of termination, we shall have the charge, and this charge, of course, positive up and negative down, and this charge will create the electric field, like in capacitor, that will direct opposite to polarization, and actually it will prevent creation of the polarization. This is called depolarization field, and this is exactly origin this coupling of polarization with electrostatics. The depolarization energy due to this field is very huge, and it creates so-called depolarization paradox, because this actually properly calculated, the energy appears much larger than energy of condensation of the polar state. And in principle, strictly speaking, the ferroelectric cannot exist. So this depolarization paradox, which was noticed a long time ago, and I will speak a little bit further about it. So if we take into account all of these phenomena, we can write, let's say, more realistic type of functional, of Ginzburg-Landau functional, that describes the situation. So now, ODE parameter has multiple components. For instance, here it's not even, for instance, 3 components. So we shall have at least 2 fourth order coefficients, 3 or 4 third order coefficients. So we should play with all of this degeneracy. Now, since our objective to consider the non-uniform state, we should have the gradient coupling term, which for cubic lattice it will be 3 different gradient terms. One should tell that in principle, the statement of Landau that ferroelectrics are very different actually this is already all of the difference formally is contained in these coefficients. And for most non-ferroelectrics, these coefficients are known because it's very, very hard experimental work to make the fitting and really to find these coefficients. But some of the ferroelectric, especially perovskites, they were characterized, but unfortunately for some another also very interesting substance, these coefficients are unknown, and sometimes the people start to calculate it by ab initio, but they make some guess. Everybody believes this, but it creates some, but it's not tested experimentally. So this creates some loop.
What are the
Which U? Sorry. In this here. I will just go to this line. So I am now at the first line. So the gradient term. I will go now to this point. I will go to this point. I just explain now the first line. So to epsilon, I will speak in a few minutes. So a gradient term, and this part of the function now would be enough if we neglect the long-term interactions, but actually we should add here the, as I told, the interaction with electric field and also the elasticity. So what is written in the blue circle is the electrostatic part, and in the yellow circle is the elastic part. So let's now go to the electrostatic part. So we have interaction of the electric field with polarization and self-energy of the electric field, which is produced by the charges and can be also some external field. So concerning the partial equation about epsilon, so epsilon 0 is the electric constant of vacuum, and epsilon b is a so-called background dielectric constant, which is because of the displacement of the nonpolar atoms. Because, yeah. Not uniform for what? No, epsilon does not depend on the position. It's uniform. Both, yeah. How you will remove one derivative? Yeah. Yeah. Nabla I phi. No, you cannot remove one derivative because you have also the gradient term. This is the point. You cannot do this. Yeah, you can do in this case. You will have strongly non-local terms there. You can write also with in terms of Green function. Yeah. And now, so this is the electrostatic part, which gives exactly this type of non-locality that is very, very difficult to treat. And another part is the same elastic type coupling of now it's quadratic over polarization and linear over the strain tensor. So well, we have a lot of now and electrostatic energy. So C is elastic opulence tensor, and Q is the electrostrictive coefficients. Your question. So also it is assumed that they are taken from experiment, but it's not always available. And again, we can also, as Pasha suggested, we can in principle write it in the notebook. Important for what? This one. It can solve some integral form, yeah. Yeah, yeah, exactly, yes. Yes, it's important. I will show you it's important. It's important because here we have strong nonlinearity and it's coming in play. So this is actually the most general way to describe, but it looks quite complicated, and all of my talk after, I will speak about some particular cases, and you will see that the situation is very rich can be very rich depending on the situation. So actually another way that can be somehow qualitatively applied, but I mean we are, or possibly I'm in the very, very beginning, so it's mostly some ideas that real solutions, but it can give us some vision. And this is also the answer, thank Pasha for some of your questions. So actually, if you're now looking, of course, Devil is a constant. And as I told you, the depolarization energy is huge. It's enormously huge. So the answer is that the system are trying to do everything to avoid the charges. So all of other energies, they are much less. So in principle, at least from my experience, there is some hierarchy in the energies. And for the first, the system always trying to have the situation without charge. So qualitatively, the system, and I will show you after the results, they always trying to arrange itself to have the divergence P equal to 0. That's, I think it's the nodal field that Pasha mentioned. And for me, this is the most important. So as far as functional is very complicated, the idea is that first of all, consider the divergenceless field. On the background of the divergenceless field, consider another part of the Ginzburg-Landau function as perturbation. So, and also they have some hierarchy, but after it depends on the situation. But of course, if you are quite far from the transition, so we are in minimum of Ginzburg-Landau functional, so polarization would like to be as much as close to the uniform value. Of course, after coming the minimization of gradient energy, anisotropy effect, but for this case also we're trying to look for the less anisotropic system to not mix everything together, and finally also elasticity. So, but the idea to describe qualitatively, it first is to state that the polarization field are solenoidal. So just let me now give you some, it's our old work, but some example how one can see very interesting phenomena just from electrostatic of the situation. So this was really experimental situation, and this was experimentalist who called me. So now it's not for 5 minutes. It's not anymore perovskite. It's some kind PVDF, TFE, I don't know what material, which is uniaxial ferroelectric, and even more the background lattice is has no. I mean, it's completely. You have no high symmetry axis. It's absolutely low symmetry ferroelectric with up-down directed polarization. What they observed the domain that created after star moment becomes hexagonal. There is no background hexagonal symmetry here. So actually we have the number of 6 becomes some kind of magic, because why 6? They called me, asked me, explain why 6 is universal number. There is no reason that we shall have the 6-fold symmetry. I was looking, first of all, in Google, and really I did not find the just spontaneous broken off symmetry of some continuous symmetry that will give us 6. Of course, you can have the 6-fold crystal, but in this case we have the packing in the lattice. But we have here the object which have just one object that have 6-fold symmetry. Only one thing that I find is that it was now it's not related with my talk, but it's Saturn's North Polar has also 6-fold symmetry. This was found by 2006 by mission of Cassini. Also no really no reason why it should be number 6, not 5, not 5, and not 7. Even interesting is more interesting because, well, it was some publication of Nature. The people claim that they explain the six-fold symmetry, but it was very sophisticated numerical calculations, but not really physical explanation. Yes, it's a cloud in the Saturn atmosphere. It's some kind of cloud. In Saturn. If it is covered, possibly they form the lattice. Even random. Yeah. So again, the number 6 is. I do possibly it's also in some kind of dynamical formation. I don't know actually. No, I don't know nothing about this. I just tell us an example, and I did not find the explanation. But even more interesting, no, it's Saturn, but even more interesting that actually it was discovered by mission of Cassini, 2006. But in 2013, actually it was couple of the amateur from Australia that in their amateur telescopes they confirmed that. So it was not necessary to send mission to Saturn to observe this. Possibly Galilei even observed this, I don't know, but possibly nobody believed to him because really by very primitive methods they observed the things that as far as always my colleague experimenter tells that they need some synchrotron to confirm something, but I have some belief that usually X-ray machine should be enough, but nobody will believe it. It was done in X-ray machine. Okay, so it was somehow, but now let's go back to to this story. In Saturn? No, it just created one domain, and they wait some time and became hexagonal. So it was artificially created domain. It was some relaxation time, and after it became hexagonal. So actually, some plausible explanation is as follows. Let's consider domain, and we have positive depolarization charges at the top, at the bottom, and in this sense, as I told you, because of this depolarization field created by charges, it is equivalent to capacitor. So, of course, it's important the edges of this capacitor, so we deal not with ideal capacitors that we studied at school, but with real capacitors that we also studied at school, but really did not pay attention too much on it. So actually, the real capacitors formula was done in the last or before last century. It is called sometimes of Kirchhoff formula, sometimes by Lorentz formula. I find two references. Not clear who really was the first. I did not arrive to find not these publications, but historically it would be very interesting. Really, was it Kirchhoff or was it Lorentz? Who did what? Because the references are very different. But here's the formula of the real capacitor, and first of all, we have the usual energy that we studied in school. And also we studied, possibly university, it was some books, some corrections because of the edges of the capacitor. Two very interesting things we can observe here. First of all is the sign minus, which means that this correction is negative. And the second important fact that the energy, it's not only the energy of the surface. I mean, it's linear over air. I mean, this is written for circular capacitor. So it's not just the perimeter, the length of the circle, but we have some contribution in the logarithm. So it is not the local term. it is not, like one cannot tell that the real energy of the body. And this R means that because it's not local, that the energy is very dependent on the shape of the capacitor. No, here epsilon, no. So here is a capacitor with epsilon equal to 1. Yeah, okay, so. No, see, this is not ellipse. This is circular capacitor. R is the radius of the circle. No, sorry, I told this, but unfortunately it's misleading with yes, it was square, of course. And yes. I'm very sorry for this. Yeah. S is the area. Yes. P r square. Yeah. So, but again, it's important that 2πr is the length of the circle, and it's not linear over the length. You have some additional contribution of r. So, from this term, it means the following: that imagine that the electrode of capacitor is not solid; it can deform. In this case, of course, the electrode of the capacitors would like to have this term as much as possible, keeping the area the same. And exactly this energy will be important for us further. So again, I just told the negative sign instability towards the shape deformation. In this case, at least it would become ellipses, but possibly more complicated figure. Also non-local characters that come in control the shape of the deformation. So more profound study of the Lorentz-Kirchhoff formula was done in '68 by Tilly, who was working in Bell Lab, and he obtained the corrections of the deformation of the circular capacitor for different harmonics. He obtained all the coefficients inside deformation, and he demonstrated at which condition which harmonics becomes more, and at which parameters. So they are not always stable. There are some stable, unstable. First of all, of course, the most unstable will be ellipses. But he obtained this approximate formula considering the deformation of the capacitor as a perturbation. And actually, this is what we're supposed to now to do, because as we understood, the ferroelectric domains is nothing more in this electrostatic approximation as capacitor. We would like to use this formula really to see what kind of instability we shall have, based on our idea that instability should appear. Toward deformation from the circle. No, I'm now talking already about ferroelectric domain. And capacitor is fixed, so because of this, capacitor cannot deform. But ferroelectric domain can. Okay. Yeah, but I did, of course. Of course, but I did first thing that I told them. My hypothesis is the electrostatic is the most important thing. This is assumption. Yeah. All other term can be dependent on the situation, feeling, intuition, and so on, can be used as a perturbation. Yes, yeah. You can see. I'm doing a little, no, not. I mean, sometimes I take in some arbitrary term from this. I tell here is a perturbation, but I have some feeling and some experience which term I can use. But
there is an assumption that all the domains are parallel somehow.
No, here we have only one domain, which was artificially created. Okay, so exactly, possibly. I will answer, but after I will show to Pasha, but I will show. Here we have one more parameters, is the energy of the domain wall. But I will discuss it later. Sorry? Delta R, where? PH cube. I don't, actually this formula of Tilly, one should look for the article. I don't know why it normalized by H. Already I don't remember this. Yeah. No. So now, the problem is that in Kirchhoff-Lorentz formula, epsilon equal to 1. And we deal with ferroelectrics in which epsilon is quite large. So there is some generalization of the, and I never saw the Kirchhoff-Lorentz formula for the case, for the so we needed to generalize the Kirchhoff formula. This can be done because we consider it's a kind of textbook problem. If we have two dipoles that are at ferroelectric slab and they interact with each other, what will be the energy of interaction? So the energy interaction can be when we have some epsilon inside. So this is done by different way, for instance, by image method, and we can obtain the energy of, so this is two dipoles if epsilon equal to 1, and one can actually make summation of this formula, which NH, because this is some kind of image method, to see what will happen in if you have the dielectric slab between them. So this is purely technical electrostatic problem. Finds that it has quite a compact solution. And finally, we can generalize, by the same way, we can generalize Kirchhoff formula for the, so actually we can do mapping from vacuum to dielectric capacitors also by the same type of consideration. And finally, we can, by such type of summation where V1D is a Kirchhoff formula for epsilon equal to 1. So every epsilon is here in beta. And finally, after some kind of summation, some kind of mathematics, we can obtain also the generalization of Kirchhoff-Lorentz formula for the finite epsilon capacitor, but with finite epsilon, so which is good because nobody does this, but we needed to generalize it for the for our case, and actually this is as the answer of Pasha question. Pasha is away. So we consider this WD as the Lorentz Kirchhoff energy. PE is interaction with the electric field because also it was some internal built-in field. And what is not coming from electrostatic is the domain wall energy with just some given number. So when we put everything together, after we completely repeated the Tilly consideration for the kind of instability and recalculated all of the term if we are doing some trying to do different harmonics, and possibly it's even here is better. I don't know which formula is better. And finally, we find the correction coefficients to all of the harmonics. Actually, this is kind of mathematics formula that we obtained hereafter. I will show you the result. So we were looking for second variation with respect to harmonics with number k, And we were looking at which conditions the harmonic with number k becomes unstable. So this is the result of the instability. So for different harmonics and for different aspect ratio, we have stable region of harmonics and region that harmonics become unstable. And actually, this result was presented to experimentalists, and what is important is that harmonic number 6 has nothing particular in this story. Depending on the aspect ratio, we can have different type of instabilities. Well, after this experimentalists, they were looking, and indeed they find 4 and 5. So this is the result. And for the given aspect ratio, they really find another. They were looking more attentively to the experiment, and they find also the different type of instability. So 6 is not a magic number, at least in this theory, but we see that electrostatic really can, only electrostatic can play a lot in the physics of ferroelectrics. Moreover, because what we have instability towards break of the initial circular symmetry. After certain conditions, they find even they obtain some fractal type of the boundary between domains, but this story needs to more sophisticated, or needs at least time for calculations. But at certain conditions, even it can become fractal because at given area, in principle, domain try to make safe as much as possible. Of course, this problem is not purely stable; it's dynamical picture, so there are a lot of very interesting things to study here. But now let's go back. So this was just story to illustrate how the electrostatic is important in the physics of ferroelectric. And we go back and we go to well, we're already at nanoscale, but important is that at nanoscale we have principally non-uniform, non-uniform topological state, because we have, by definition, we have non-uniform distribution of polarization, which is interplay between confinement or geometrical confinement, boundary conditions, and electrostatic. And in principle, we can have different symmetries of the object, from nanoparticles, nanorod, nanocylinders, 2D geometry, and so on. But here we should possibly, I can tell possibly the answer why ferroelectrics are not so much studied as, for instance, magnets, whereas the physics of electrostatic physics seems to be very interesting, very fundamental. Actually, it's kind of rumor, but the people told about Batra and Silverman, who were working approximately at the same time in Bell Lab. And at the same moment, they wrote some article in which they claim they studied the ferroelectric films, but it's always valid for any other nanoscale object that below a certain critical thickness, the ferroelectric polar state is thermodynamically unstable. And they estimated the critical thickness for TGS, it's also another type of ferroelectrics, at 0.5 microns. So the statement was as follows, that when we go to the very small scale, the ferroelectricity will be killed. Why is it all this? Actually, they told this because they did not know the background physics that was done much before. And they were based on this depolarization field paradox. They just calculated the polarization field. As they discovered the things that LandauLifshitz told many years ago, and they told how really one should treat the such situation. So this is famous 180 domains that were discovered by LandauLifshitz, and that call in the literature is Kittel domains, because Kittel published it in 46. So, but as I told, the story was completely forgotten. Batra Silverman, who were working in Bell Lab were study the question, can they do ferroelectric memory or not? they believe to this theoretician that one cannot go to nanoscale, they completely closed all of the work on ferroelectricity. Well, of course, if will not publish in Nature, nobody will publish in parallel. After, nobody will publish in solid-state communication. And in the whole world, in 90s, the laboratory of electricity were closed. Only few people, they survived during this policy. The people who survived till 2000s, they started the new physics in ferroelectrics that were coming with ferroelectric nanofilms. It was experimentally shown that ferroelectricity exists till even atomic scale. So what is the problem? Actually, the problem was the problem of Butler and Selman. The problem is that there are these depolarization fields. So the depolarization energy is huge, and in principle, it should kill. In macroscopic samples, usually all the experiments were done either with electrodes, or it was done some charged ions that were coming from the air, and they screen the depolarization field. But when we are coming to nanoscale, one can show that because of the finite lambda, the screening will become less efficient. And actually, the answer of actually this, I think everybody who was passing the Landau minimum knows this problem very, very well. This was published in 37, and after LandauLifshitz posed this famous problem in the theoretical physics book volume number 8, that because of the depolarization effects, the magnet, but for ferroelectric is even much more actual, it will split on the domains. Indeed, when we have a monodomain sample, we have this very, very bad depolarization field that will kill ferroelectricity. To give you idea about the effect, we can quite simply calculate the renormalization of the critical temperature to, for instance, for ferroelectric with transition temperature, let's say, of 300 Celsius or Kelvin, it's not important. We can calculate what will be the renormalization of TC when we take into account the depolarization field. And we obtain the transition in ferroelectric will occur at minus 10,000 Kelvin. So this is how huge this effect. But again, the macroscopic sample ferroelectricity exists because we have some external type of screening. And actually, when we remove all of the screening, according to LandauLifshitz, the system will split on the domains. What will happen in this case, the depolarization charge will be concentrated at the surface. In this case, of course, the depolarization field will not penetrate inside of the material. They will be at some finite thickness layer, and the thickness of this screening layer is the order of the period of the domain structure. But of course, the price that we should pay is the creation of domain walls. But finally, if we doing the proper calculations, we obtain the right critical temperature that possibly will be, I will show you now the phase diagram, and we obtain that really we can absolutely have till the several nanometers. Several nanometers just because below the Ginzburg-Landau approach is not working, but till the thickness we shall have the perfect domain structure. So we do this in 2005, and nobody believes this, and this was still this belief that we have no domains, we have no ferroelectricity, and so on and so on. Actually, the experimental proof of existence of ferroelectricity with domain was done by Pavlo Zubko. He was working at the time in group of Triscon, so with his collaborator. It's not easy, first of all, it's not easy experimentally to show the ferroelectricity because they have no influence on optics. They not very well coupled with elasticity. So for experimentally, this is challenge to demonstrate the ferroelectricity. What he did, he just demonstrated that the usual Bragg peaks have some satellite. So he demonstrated the existence of the superstructure, which he associated with domain structure. After now, there are, and I will show the development of the situation now. So now it's possible by different, quite sophisticated synchrotron method to visualize this lattice. So this was our prediction in 2005, the renormalization of the critical temperature. So you see it is renormalized, but not so dramatically as it would be for monodomain sample. And another interesting observation was that, so actually we call this a soft domain. Soft domain, actually it's not really domain which is was assumed by LandauLifshitz, Kittel and company that exists in magnets. So in soft domains, the polarization changes gradually, like sinus-like profile, in both directions, across the film and in the film direction. So, but which is quite natural if you are looking for TC. But what is important is that because we have some scaling of equation, in principle, soft domains should exist as the very thin films. The domains should be always soft. So what is the difference between which we called hard domains, Kittel domain? We have polarization, which is constant, and soft polarization, really, it behaves like sinusoidal profile in both directions. So first of all, this is the thickness of the film. So first of all, polarization changes periodically, but not sharply, but quite softly in the direction of the film. And also the polarization goes to zero at the film surface, which is not the boundary conditions. This is just a question of minimization of the function. So the system would not like to have the depolarization charge at the surface. Actually, it's very interesting because actually this is another story of so-called Landau-Lifshitz paradox and Landau-Lifshitz fractal branching. Because when Landau and Lifshitz discovered that the system, magnetic system, should actually split on the domains because of the depolarization field effect, they considered what happens near the surface. And finally, they discovered that the field, which is not penetrate now in the bulk, it's still very, very high at the surface. It's higher than the coercitive field. And because of this, they told that in principle, close to surface, the polarization should reverse its direction. And after, if you consider the smallest, it should reverse again, again, again. So in principle, in the ideal system with infinitely thin domain walls, we should have so-called fractal branching of domains. There were even several claims of observation in magnet system. I think in superconductors, they really observe such type of branching. But actually what we claim is that what we have now is another solution of the Landau-Lifshitz paradox, because in Landau-Lifshitz they make the assumption of the constant flat polarization, and in case of the Ginzburg-Landau, the polarization can change its modulus. So in principle, the polarization is coming, so the charge is not only concentrated at the top, but it can penetrate also inside of the sample and gives another solution of the paradox. So no fractalization, just to have the softening of the polarization, PZ component of polarization in the wall. So this was the state, and it was more or less quite sleepy atmosphere till 2016, when Nature journal started to put attention on this effect, namely a group from Berkeley. They already, because experimental technique is developed very, very high, now they really able to observe the displacement of the individual atoms. They claim observation of polar vortices in oxide superlattices. So in principle, they observe exactly this structure, and they claim that we have some kind of vortex structure in ferroelectrics. Very, very fine. Actually, it's now this question also about the terminology, but this vortex is not vortex alone. It is really the periodic structure of vortices, antivortices. For me, this is the same as the soft domains that I just told now, because actually following Landau-Lifshitz approach, what we consider the polarization as an order parameter, but to this order parameter, we have also some kind of induced polarization, because distribution of polarization, it creates depolarization charge. Depolarization charge creates the internal distribution of the field that close to TC it's penetrate quite, somehow penetrate. And this field created by polarization, it will create also the induced component of polarization. If we add to the real order parameter the induced part of polarization, we obtain the vortices. So vortices really is the same time as this kind of soft domains, but in soft domains we consider only the spontaneous polarization, and the vortices is a mixture of spontaneous and induced polarization. As theoretician, I prefer mostly to speak in terms of the order parameter, but not of the order parameter plus induce something. But vortex, anti-vortex, yes. And this is actually why I don't like to call it vortex, because you cannot separate vortex alone. You always will have size. Yeah, of course. Yeah. But, well, it's already the question to Okama and company. So, and explosion 2019, the people draw a lot of pictures that are supported by experiment. And it's now 2019, it becomes a subject at least of 3 Nature publications. They observe really more sophisticated structures of these vortices. Sometimes they form really not, they form not really the stripe structure, but they form the point-like structure, but this is well known in magnetism as a bubble domains. Yes. No, it's purely electric, no magnetic field at all. But electric field plays the role of magnetic field in ferromagnets. And what I'm claiming is that the role of electric field is much stronger than in magnetic systems. So here this effect becomes much more visible. Dielectric, it's perfect dielectric here. Well, a little bit semiconductor. I will tell you I don't remember, because for my calculation dielectric, but I have this number.
One would imagine there is a current flowing.
No, you have not current. You have, because, no, you have not current in dielectric, and it's polarization. Another question, because it's not rotor M, it's rotor P, rotor polarization. But what does it mean, rotor P? For me, this, if it is massing, or there is some physics beyond of this. I don't know. Maxwell did not tell the answer, and I did not find the answer in the literature. What is the physical sense of rotor P? Because this is a quantity that really appears in a lot of our theoretical approaches.
What would be the topological charge of this electric flow?
Rotor P, yes.
It's not quantized.
Not quantized, no.
Classic.
It's classic. But several people discuss the Berry phase, the possibility of quantized, but it's still to discover. No, I mean, nobody told about it is quantized, but I mean, several people speak about some kind of Berry phase in the unit lattice with polarization, and this can be, I don't know.
Is there any relation between this polarization and Berry phase?
Yes, there is some Berry phase in the wave function related with the polarization. I don't understand this. Possibly we can discuss if you understand the Berry phase of the psi function. We can understand it together, but I tried several times. I did not arrive.
This level is only classical.
It's classical. Up to yes, now it's classical. Yes, but there is some indication of quantica, but it's not very. Again, the problem is that community too small, and they not have a lot of expertise really in the high level physics. But they produce a lot of very nice pictures now. Part of them experimentalists, part of them modeling, and so on. And this one, actually, this is they call skyrmions, because they also observe that the vortices are coreless. And this is top view of this kind of, so it's bubble domains. So because now, suddenly last year, very large flux, people start to work on this. They sleep for 20 years, and now they wake up. So of polarization. Yes, yes, yes. Exactly, yeah. Again, but still, here the most important, the driving effect is electrostatic. In magnetism, also you have this demagnetization. I know. I'm not very high expert, but I will speak about another formation. And now, who are working with magnetism and all this stuff, they are involved in the Zaleshinsky-Moria chiral term. Here you have no, not yet, chiral term. All of this stuff is produced only by electrostatics. I believe that not. So, I mean, now the problem now is that there is some war of definitions on the level of definitions, not on the level of physics. And for instance, Yakov asked, he was absolutely correct, is it vortex that you cannot have only one vortex? Now they call these bubble domains, which is quite also known in magnetism, they call it as a lattice of skyrmions. One can ask them, produce please one skyrmion. It's impossible, it's unstable. But they have lattice of skyrmions, so you can yeah, so actually this was in one ferroelectric layer of multi-layer system. You have para-ferro. One assume in principle that each layer independent, and each layer you have such type of picture. After, of course, you have some coupling and so on, but you can, here you can think that you have just only one layer. And as I told, the situation is 50 years ago this was done. In magnetism, superconductivity situation is somehow repeated. And when we just started to do research, nobody even believed of existence of ferroelectricity at this scale. So now let's talk about about another aspect. About switching, topological. Some another story which I think quite funny. I did not find in very simple, but I did not find in literature. It's a multi-bit logic. So first of all, let's go away from any topology and just consider the cubic ferroelectric, which is cubic ferroelectric deposited in some substrate. So substrate produce some internal tension, so we can have either tensile tension or compressive tension. So polarization, we lose this cubic symmetry, and we can have, actually this is classical work, very good work of Pertsev, Tagantsev, the Bilgotov, done in 98, also before all this boom in ferroelectrics. They just considered the phase diagram of the system, and if you have the internal misfit strain introduced by substrate, you can have loss of the symmetry either up, so we can have so-called C polarization, which is just uniaxial type of polarization, or we have fourfold degeneracy in plane, which is called AA phase, or sometimes we can have direction of polarization in the diagonal. I using it because this is the most classical examples in physics of ferroelectrics. I mean, new era of ferroelectrics, of ferroelectric films that strain